All right, so I think we are set. Should I use this one? Yep.
Yeah.
Okay, so I think we are all set. So it's a real pleasure for me to come in front of you here in Porto on React Native Porto edition, the second edition, with my talk, which is titled On-Device LLMs Done Right in React Native. So before we start, let me quickly introduce myself. My name is Artur Morys-Magiera. I'm from Poland. I'm a senior React Native and AI engineer at Callstack, also a PhD candidate in robotics at AGH University of Krakow. And yes, well, let's move to the agenda. So as you already know from the title, well, there is nothing hidden in the contents of this presentation, but let's quickly revisit the agenda. So I envisioned three primary sections. Firstly, we can talk about why even bother with running LLMs on device, because we can just connect to the API and use Claude or whatever. Then we will talk about the aspects of this from the user's side. We'll move on to the choice of libraries. So what's the current offering of open source, what's to be used, what are the use cases for those, and when which solution wins. And finally, we will take a look at the developer's perspective, so all the technicalities, the problems, the challenges from this side. And before we dive in deeper, maybe just a quick disambiguation, because nowadays many people say it's AI, right? And that's what we are doing. But actually, there are a few categories. So we have the artificial intelligence, AI, which is a subset of a few categories. We have machine learning, which does not only have LLMs, because it's a nested category, it has many other methods. There are supervised, unsupervised ones for grouping, for clustering. There are gradient boosters, support vector machines, logistic regression, all sorts of methods that we can reach. And a subcategory of this is deep learning. And this is actually the category that encapsulates all the neural networks, all models that have more than one layer. And here we have models for vision, for speech recognition, for text-to-speech, and of course image processing, and of course the LLMs, which will be the topic of today's talk. So we are actually not using, of course we are using AI, but we are using precisely LLMs, and yeah, this is the disambiguation. So what would we even care, since we have large language models that have hundreds of billions parameters in the cloud? There are a few reasons. The first could be the offline experience. So imagine we have an app that, for instance, the users typically don't have access to the internet, or we may even consider the economical standing point. We don't want to waste money on the tokens to provide these services for the users. And we can leverage the power of their local hardware, so of the power of their devices to run this inference locally. The second aspect would be privacy. So if we would use any kind of API, any kind of service to run this inference in the cloud, then we would basically have to deal with the GDPR, with all the data processing issues. And if we run it on the device, the data never leaves the device. That's as simple as that. The last aspect is latency. So we will not experience any problems with the latency other than, of course, the limitations of the device, because everything will be running locally. So we are not dependent on any network conditions or maybe the condition of the inference provider. And there are three problems actually, on the other hand, because it sounds like a perfect solution, right? But there are a few aspects that we need to take into account. So firstly, we have the aspect of the user. So the models actually weigh. They are pretty large. They tend to be pretty large, as we know. And the ones we can run locally are much smaller than the ones we get from cloud inference providers. That's for sure, because we don't have as powerful hardware as they have. And we have a few different solutions to this. We can quantize the model, which is a level of optimization, a method of optimization of the models that is lossy. So, well, if we quantize it, we somehow lose some of its power, but at the same time, it's much more lightweight, both in terms of storage and inference. Well, the user will also want to check what amount of memory our app uses. And if our application weighs, I don't know, 30 megabytes, but the model it uses weighs half a gigabyte, 1 gigabyte, 2 gigabytes, then the user will ask, well, why is my memory full? So we also need to take this into account. The second aspect is hardware support. So it may be that the device the user has, especially if it's a low-end device, is just too weak to run inference of that model. So, for instance, the simplest problem we may experience is that the model doesn't fit into the RAM memory. Because it's just too large, the user has, I don't know, 2 gigabytes or something like this of RAM, and the model won't fit. Secondly, there is the acceleration support, because, well, all those models have to run somehow, and these are just matrix operations, a lot of them. So a typical calculation complexity of a matrix multiplication is all n to the third. So this is bad. We can try to parallelize this, and this is where GPUs and NPUs come into play. GPUs, the graphical processing units, NPUs, which are kind of specialized devices that are even better in accelerating this. And while we usually have tens, for instance, 16, 32 cores in a CPU, on the GPU we have thousands of them. They are much, let's say, less powerful individually, but they can process parallelly. And in this sense, we can parallelize all the calculations. But, of course, we need to have hardware that supports this. And this is one other thing. There are, of course, accelerators such as Apple's Core ML or MPS on desktops. There is Qualcomm's QNN for Android devices. And of course, even if the user doesn't have any NPU, we can still utilize the CPU with some SIMD, so single instruction, multiple data, vectorized operations that are still more performant than we usually would do, provided the framework supports this. And I have an example study because usually these libraries all have some, let's say, handicaps in the sense that you can, for instance, use an abstraction that allows you to support a wide range of GPUs, wide range of devices with a single implementation. One such thing is OpenCL, which you can use, which is a library that is an abstraction you can use to do matrix operations, for instance, on these devices. And this is something that, for instance, MLCLM, one of the libraries that's used for inference, uses underneath. And the screenshot we see here is a Perfetto performance trace from one of the runs with a Llama 3 to 3 billion parameters model, where actually underneath what's used is the OpenCL framework. And typically, this is how an inference of a model would look like. So starting from the left, we would see the prefill phase, which is basically pre-allocation of the buffers. Then we have a TVM synchronized. TVM is it's Apache TVM. It's a library that's used for low-level operations on the GPUs. So we can consider it part of this pre-allocation. And then we actually have the inference. So this here is softmax. It's the layer that actually calculates the probabilities of the tokens. Then we have decode. So we are decoding the tokens from the numeric format to actually strings. And all these blocks here, the stacked ones, these are actually next tokens because an LLM produces token by token, and that's why we see more of those. For the first time, we have something we could call a cold start, so all of this takes pretty long. For the next, for all subsequent tokens, it will be much shorter. So this is how it looks when it works. And yeah, I actually had the arrows for this, sorry. And this is exactly the same model, exactly the same code, but just running on a different device. And it's not diametrically different, it's just a different vendor of the GPU there. And well, as you can see, it's crazy because this pre-allocation phase reached 47 seconds. It was a total bug. It actually froze the system UI. This happened on Android on a few devices. And as you can see to the right, we still have pretty good performance after this phase, but well, who would live with a 47-second freeze? So when we actually tried to debug this deeper, it turned out that while you can use an abstraction layer like OpenCL to abstract away all the things and support a large variety of GPUs that just support OpenCL, the vendors should provide the drivers for this one, and many do. Well, this also has some problems. And this was not a bug that was a fault of the library or something like this. It was just a coincidence that they had two formats of the models. We sorted this out with the maintainers. It turned out that the difference between the two formats was just that the matrix of weights was transposed. So the only thing that the library had to do with one of the formats was first transpose, then just use the weights. And, well, the transposed version caused this. And only on a subset of devices. It was just a coincidence that probably some of these operations were inefficiently implemented in the vendor driver or something like this. We don't precisely know. But just switching the format of the model with this transpose matrix helped, and, well, it just worked just as smoothly as it usually would do. So this is, let's say, the other side of the medal, as you would call it, when using those abstractions layers, that they work well until you don't know why they don't work at all. And this is one of these cases. And yeah, this is the conceptual level of what I was talking about, so how LLMs generally work before we advance forward. So typically we just have a prompt that passes through the encoding level. We get tokens, and tokens, well, maybe words, maybe pieces of words, something like this. It depends on the tokenizer. And then we generate embeddings, which are vectors, as many vectors as tokens we had before the embeddings layer. And these vectors of numbers, these tensors, are passed into the transformer itself, which generates logits, which are weights that correspond to possible tokens that can be output by the LLM. We should sample them. So this is a fancy word for just picking the, well, according to our heuristic, picking a token that we would like to output as the next one, so the one we think is the most probable to be output next. And finally, we close the loop, so we concatenate the prompt with the, so all the chat history with the token that has been output, and we can make the, start the inference over. Yep, so moving on to the practical part. What libraries are offered in open source? And, well, maybe let's start with such a question. Is there one library to rule them all? So should we just pick one? The answer is no, of course. It depends on your use case. There is a ton of, or maybe not a ton, but a reasonably large set of those libraries. And, well, they have, all of them have trade-offs, all of them have their use cases. So one of those is React Native Fast TF Lite, which is a wrapper for TensorFlow Lite, which has been renamed recently into Lite RT. Well, the model distribution is such that you store the models on device. You can do this generally in two ways, and this will be the same for most of these libraries. So we can either provision them over the network, so the app will download them from the server, put to a temporary directory or to a cache directory and load from here. Or you can package those models within the application, so the experience is better in the sense that the user opens the app and it's out of the box ready to function. But in such case, well, the application also weighs probably a lot, unless you are deploying small models, for instance, for vision or something like this, which can weigh a few megabytes. Yeah, and TF Lite itself is really good in the sense that it has good support for different hardware. It runs on the GPU using Core ML, using Metal, OpenCL, which I mentioned, OpenGL, and an API, which is an API for NPUs on Android. And of course, it will run on a bare CPU if none of these is available. The API for usage is custom. So this is one problem we'll probably see with all or most of these libraries, that there is no standardized common API that you can use to consume them. And yeah, of course, the platform support is both iOS and Android. Then we have Onyx Runtime React Native, which is, well, it captures a different segment in the sense that it's a low-level inference library that doesn't, that also, just like LiteRT, allows you to run any type of model. So you're not only limited to LLMs, you can use anything. You can build your own small vision model, for instance, or a classifier, and just, you know, just pass it array buffers or tensors and get the results. Hardware acceleration is also wide, so we have QNN, which is Qualcomm's API for Qualcomm devices, and an API, as previously, CoreML, XNNPack, which is a library for SIMD operations on the CPU, so it will be slightly faster on the CPU. We have support for ARMs, for the ARM CPU's neural network API, and Apache TVM, which also has a wide compatibility. The API, again, is custom. Then we have React Native Executorch, which is a wrapper around Executorch, which is Meta's project for running Torch models. And well, here the distribution is the same. We also have models stored on device. It's our duty to provision them. And the model format supported is GGUF, which is a standardized format for LLMs. We can also use others. Acceleration is very similar, and device support is iOS 17 and above, Android 13 and above. And there is also a different library, which is called React Native AI, which we maintain at Callstack. And the difference with this is that it actually is a set of packages that you pick from. One of them is React Native API/Apple, AI/Apple, which is a wrapper around Apple Intelligence, the Apple Foundation models. And here the provisioning model is totally different because you can't provision your own. You use Apple Foundation models. And the difference is you don't need to provision anything. You don't need to take extra space on the user's device because the models are provisioned within the system. So the user won't be feeling the weight of this app. However, this comes at a cost because you are limited with the standard limitations of Apple Intelligence. To these belong, firstly, that you have a preset of models that you can choose from, so you can provision anything. You can use only the ones that Apple offers. Secondly, there is a limit of context length, and the context length is 4,096 tokens. So that's not very much. Oh, sorry. But yeah, that's at the cost, the cost of having system provisioned models. There are, of course, tools that can allow you to still break through the token limit, because if you would just pass too many tokens to the prompt, then you would get a crash or an error because you can't just pass more, you are exceeding the context window size. But you can, for instance, do a sliding context window. There are tools that Apple offers in a package that he actually announced on the WWDC a few days ago. And we are also planning to support this one. And the difference also is in the API, because we built it such that it has compatibility with the Versal AI SDK. So if you are using it, for instance, on the web, you may probably know it well. And you can just bootstrap the model with any of the packages that we offer, for instance, this Apple bindings, and then just use the Versal AI SDK API to interact with the model to run inference on it. So just as you would do this on the web, for instance. We have also other packages. They are also exposed under the same Versal AI SDK compatible API. One of them is React Native AI/MLC, which is a wrapper for MLC LLM. You can see the demo to the right. And yeah, this is a fully locally running in offline mode model using MLC LLM. The difference between MLC LLM and others is such that it has its own converter and its own optimization engine that optimizes the models as you package your application. All this happens at build time. It has operator fusing, so I will probably jump to that on the second slide, on the next slide, or memory layout optimizations. So this is also a pretty good solution, and this differs, of course, from Apple Foundation models, such that the models are again stored on device, so you have to provision them yourselves. Hardware acceleration is through OpenCL, Vulkan, and CPU. And, well, yeah, that would be it. All right, and the optimizations. So many engines have them. MLC LLM has them. Onyx Runtime from Microsoft that I mentioned also has them. And what's that? So firstly, we can have operator fusing. And this is a very simple example of how this may work. So you can imagine that in the inference graph of the model, you could have two operations. So firstly, a division, which is 1 by x1, and then times multiplication times x2. And why waste time actually doing two multiplications? Because a division is basically a multiplication as well, while you can fuse it into one operation. And it's just as simple as that, at least in this case, because some of those operator fusions are much more complex, such as this one, which is the operator fusion for the layer normalization layer. So if you are developing networks, you probably know this layer, and it's, well, the inference graph of this layer looks like that, and it also can be simplified. Just one more example of a simple category. So if you have some condition, then a negation, and some if, then you can, let's imagine that for the true value we get action A, for false we get action B. We can just swap the actions and remove the negation node from this inference graph. And this is another example of optimization. Another package we have, and actually the last one here, is React Native AI/Llama. So this is a wrapper around Llama RN, which is a wrapper around Llama CPP. It's very similar in the sense of formats to executors here in terms of support. Hardware acceleration happens through Metal on iOS and Hexagon NPU on Android. So this is also a partial device support. And yeah, it's also a good choice. So now let's take a look from the developer's perspective. We covered all the frameworks, we covered all the things that the user will be interested in. So how does it look like from our end? So first we need to take a look at our user persona and see how many devices, how many low-end devices we have, what's the share of this. If we are targeting some users who have only good devices, for instance, I don't know, newest iPhones, we need to take a look at what we are aiming at. So are we doing a simple summarization of a sentence where probably a 300 million parameter model is suitable for, or are we, I don't know, doing coding or structured output generation in JSON format where probably we would have for Llama 3 billion or something alike? And secondly, we need to take a look at the fact, well, will the user survive us shipping a model that weighs 2 gigabytes, for instance? This is also something we need to take into account. Sorry, again. Coming back after a short break. Then we have the matter of resource usage. So is the device actually capable of running that? So we need to ensure that, for instance, we provision the application that can download 2 models from our server. And at the startup time, we check what's the RAM available on this device, and I don't know, if that's 2 gigabytes, then we are probably aiming for a 100 million parameter model. If that's 4, we can aim at 300 million parameter. If that's 12, we can probably aim for 3 billion or alike. Next, we can still try to fit in even those larger models into the RAM of those devices that we have. So if you remember the slide that I shown previously with the Hugging Face repository where we had the models, we could see that the same model could weigh from anywhere from 500 megabytes to 2 gigabytes. And it was a matter of just the quantization level. Because all of these inference graphs, they do operate on numbers. And we can easily imagine that while we usually use floats there, either float 16 or 32, depending on the device, usually it's float 16 for mobiles, we can easily imagine that we are using, for instance, integers for those operations. We will lose a lot of precision, that's for sure, but we can still try to do that. And we can, for instance, quantize our weights such that we package the model not with floating point weights, but with integer weights. And then when we unpack the model and load it to our library, we can try to do a mathematical operation to actually turn those integer compressed weights to floats. It is, of course, lossy. And, well, one of the simplest examples would be this one. I know it's not simple, but generally there are ways to lossily compress this. Yeah, probably you can skip this one. And, well, we are, of course, losing precision, so the model won't be as good as it would be when it would be floating points 16 or 32, but the model could weigh could be twice smaller. The operations themselves in the inference graph would still be on floats, but the format of the model would be with compressed weights into integers. And, well, the last matter is the common API with a question mark because, well, there's no standard and all these libraries offer something different. But at least with the ones that we provide, you can use the Versal SDK. So you can import this one, for instance, on the web. This is how you would do this on the web when you have a connection to an API. Pick the model, and that's it. And well, with our libraries, you can just import the proper backend that of your choice. You can bootstrap the model and just place it in the same code that you would do for the web. Exactly the same happens with the other libraries, because the previous slide was about Apple Intelligence, which has all the models provisioned. So it's just a matter of calling the one method and that's it. With others, you have to probably download them, or you can provision them with the application, and well, it's somewhat easier in this case. But generally, it's a few more lines of code, and then all the processing, all the inference is just as you would do it normally. The cherry on the top is we also have the DevTools. If you are using React Native, you are probably also using Rosinite, or at least probably have heard of it. We also have an integration with Rosinite that allows you to have full observability of what's happening underneath. And yeah, I'm about to wrap this up. I have just one more thing to break this, break this presentation actually. Well, yep, here it goes. So at the very end, I wanted to show a live demo. I hope it will not break as much. So this is how it would look like. The app you can see here is actually an experimental thing that I'm tinkering with since a few days or a few weeks. And what you are seeing here is actually Transformers.js library. So the one you probably may know from the web, where you can easily use it for inference of your models. But this one is actually running in React Native, and this is an Expo application. So I'm actually working right now on bringing platform support for React Native to the library. I will contribute it open source, and I'm probably finalizing it. And well, Transformers.js use actually Onyx runtime underneath. Onyx runtime also supports the web through Web GPU, supports desktops, and you can probably, you can easily imagine that you can just plug in Onyx runtime React Native, because Onyx runtime itself also provides bindings for React Native. And this is what I've done here. So let's see. Here we have an LFM 350 million parameters in floating point 16 format, so that's actually not quantized, running on this iPhone 17. Let's see if it can tell us a joke. And here we have it. It's 26, 27 tokens per second running on this iPhone. Yeah, and that would be it. Thank you very much.
Questions, guys? Anyone has questions? I have.
So, do you have an idea, like, for a real life use case for this solution? Like, imagine that creating an app that can help people, that can be used by many. Because I have an idea. For example, maybe you can tell me if it makes sense. Sometimes when I fly to Poland or just travel, I'm on the plane like for hours, and I'm learning Portuguese, and I want to just talk with the chat speaking Portuguese and explain me the rules, grammar, and so on. Do you think that this can be run, like I can use it on the plane to just learn the language?
Mm-hmm, absolutely. So it depends on how bad you can go, or how hard you want to go. So if you need a very large model, probably your desktop is the best choice, because you have a large disk space, large memory, good hardware. But you can of course run it on the phone. It's totally doable. And yeah, you can pick any model you wish. So maybe there are fine-tuned ones that are actually specializing in Portuguese, I don't know. Or you can fine-tune it yourself. I haven't checked Portuguese. But probably all of them will understand to some extent. So yes, that's a good use case. And other use cases, I would say anything that messes up with personal data or something that you not necessarily want to send to the server. For instance, I know users' notes, maybe some medical records, or I don't know, some chatbot for people that people may not want the conversations to leave their device, anything like that. And also any actually use case that's maybe not privacy critical, but also cost effective. So imagine you, I don't know, have a gallery of photos, and you have a multimodal model that allows you to search through those photos. For instance, you enter pizza or sunset or something like this. and want the application to show you only the photos that actually correspond to the description you put in. So, of course, you have to scan all those photos. You have to generate embeddings using this model, or actually the embedding model from those photos, and store them in a database, usually a vector database because these are vectors. And then when the user enters the prompt, you just run the embeddings on it. And for instance, using the cosine similarity metric, you can filter the records from this database that are very similar to the query. And this way you are actually comparing images to text. And well, this is a perfect use case for an on-device model to be run. Or you can imagine a notes taking up where you want to search through the notes or summarize them. This is also something you would like this solution to be used for. Because probably you don't want to send the photos nor the notes. And well, last but not least, you don't want to pay for the tokens on the inference side.
I think I will try with the language app, like for myself, you know.
Yeah,
to
that's
learn
a very
Portuguese
good idea.
on the plane. Thank you very much.
Thank you.
Yeah, actually, continuing on that, like with the newly announced models on WWDC, I think one of them is like 20 billion parameters, right? I think the most powerful. Do you expect many changes like in these day-to-day situations? Or for example, newbie question, but does it even affect tokens per second, or is just like a matter of context and how much the model can understand?
So, well, I didn't check the Apple Foundation models yet, the new ones. But of course, if you have a bigger model, then probably you will lose on the performance side. That's for sure. If you have more parameters, more calculations, then it will likely be slower. Regarding the context window, I think it should be set because Apple Docs mention 4096 token limit for all of the models, and that's it. But you can always fight it. You have the sliding window, which is started if you have a too long context, you can just slide a window through the context and generate multiple times. Apple has at the WWDC exactly published a set of helpers that actually offer this sliding window, for instance, utility in the package. So of course you can do it.
Awesome, thank you. One more question for Alexander.
Quick one. This is the tiny LLM world. We don't hear a lot about it, and as you are much closer to academic, how much investment there is in it? Because now I can see a real use case, and that's really interesting. Is there a lot of investment into those tiny LLMs?
You mean from the
big,
academic side, or in the industry?
Both.
Okay, so well, in the industry, I would say yes, because as I shown you, there are applications. So for sure, companies are using that. I don't know if they would be bragging about that much because, well, it's just a utility, right? They have a functionality in the application that just works. It works locally, so it's cheap, it's safe, it's offline, so that's easy. Regarding academia, well, on-device models definitely are invested in. For instance, I'm in the academic work of mine, I'm more related to AI models, but not LLMs. I'm mostly doing regression or classification, things like that. And yeah, we do this. For instance, I'm using pretty much Onyx runtime for that, on microcontrollers even. That's really helpful. Maybe not microcontrollers. Of course, you can run small models there, but probably it's closer to single board computers, SBCs like Raspberry Pi or something, or maybe NXP devices, and that's used, yes. And I know some colleagues who are also basing their research in the field of actually putting those models on ASICs, on FPGAs. So, well, this is something close to what Cerebras, the company, is doing. So you can synthesize a whole electrical layout of the gates, of the elements, of the blocks on FPGAs with the weights of your model and actually the whole inference graph embedded into hardware. And this is extremely fast, and this is what Cerebras, from what I know, is doing. Because, well, the only limitation is, there are two types of limitations, actually three, so in a simple model, because realistically there would be more to mention. First, the only limitation is the speed of transfer of the electric current, because it's physical, unless you have synchronization with memory, and then you have the synchronization matters that you do manually, or the speed of the peripheral devices that you use, because in such complex devices you probably do. And yeah, it's also a large topic. and this one actually has good prospects, but at the same time it's extremely complicated because, well, FPGAs are complex themselves, and when you mix this with AI, that becomes really rocket science.
Okay, too soon, but soon. Thank you very much.
Thank you.
Thank you, Artur. Anyone has any other questions?
Very.
Yeah. No, we have time. No.
You mentioned that these on-device LLMs, they run on the GPU. So React Native related, will that affect the UI thread? Imagining I want to be running some reanimated animations at the same time. How would that work, for example, when that 40-second freeze occurred?
Yeah,
what would happen?
This would affect. It's like with the computer, right? If you launch, I don't know, one game and it takes 50% of the GPU, you can easily launch another one. But as you're approaching 100%, you will feel the bottleneck and feel the performance degradation. And it's the same. So, well, if you spin up a small model, for instance, I don't know, a 10 megabyte classifier for a few numbers, or a classifier for images that can, I don't know, weigh 100 megabytes or something like this, then probably it won't be a problem at all, right? Because you'd use 20%, 10% of the GPU or NPU, and that's good. If you are doing it on the CPU, of course, you will probably very easily, because of the calculation, the computational complexity, you will easily, let's say, extinguish the power of this device, and you will feel that everywhere. If you are doing this on the GPU, well, if you have a powerful model like here we weren't approaching the limits, but if you have a larger model, you probably will feel it, unless you have an NPU. Because if you have an NPU, then you have specialized devices: CPU for standard computing, GPU for the graphics, and NPU actually for networks. So if it fits into the NPU, then you are good. But we still have to remember that these devices are complex. For instance, even on this iPhone, you have both the GPU, the CPU, and NPU. And it turns out that when you run a model, actually CoreML doesn't put everything, because here I had the switches. I don't know if you remember from the screen, you could pick XNNPack, which is the SIMD library for actually doing on the CPU computations. You had CoreML, and CoreML actually picks the best device for you. So you don't have control over which nodes from the inference graph go where. Some of them can be assigned to the GPU, some to the CPU, and some to the NPU if it's present. And it depends usually on the inference graph, the operations, because not all operations support all the devices, the executor devices. And also, not all data types are supported. For instance, on the GPU and NPU, you want float 16. If you have uint 8, so an 8-bit integer or unsigned integer, then it won't work though. So unless you cast in the inference graph, which is probably out of your control because this is the structure of the model, and either the model or the converter controls the conversions and all this low-level stuff, then you probably can expect that this model will run on the CPU. Yeah.
Thank
you. Here we saw, for instance, 26 probably tokens per second on the CoreML because it was floating point 16. If we use the quantized version, it's much smaller, it's more lightweight, it takes up more RAM, but at the same time, it will likely run on CPU XNNPack tops. So it will be slower.
Thank you, Artur. I think this is right in the end of the... No, it's right in the end, just to make sure we have time.
Thank you.
Thank you, Artur.